Hey, hello guys, welcome, vanakkam, vandanam, namaskaram. So it's around 2 o'clock and this is the timing that I'm starting to take video. Great. Valangiro. Okay. So last video we have discussed till current density, right? And also we have discussed till that sigma. Where is that sigma? I said I would prove that sigma is equal to sigma is equal to me squared tau by m, right? So till this formula we have taken. Okay, so we will be now proving in this video, we'll be proving what is sigma, how did this formula come, all these things this we will be proving. Okay, done. All right, good, very good. We know that Vd, that is drift velocity, is equal to acceleration into tau. So where acceleration is equal to small e, capital E, capital E whole divided by mass into time, which is tau. Okay, so this is a formula that we know, right? Okay, next is we are having that I is equal to nai v del. Okay, so in place of Vd, I'm going to substitute this formula. So I is equal to I by A. Okay, I'll just take this A in the denominator. So N E, this one, which will be E whole divided by M into 2. Okay, so I by A is equal to J. So J is equal to, okay, wait a second, yeah. So J is equal to what? N E square. Okay, so then tau whole divided by m into e. Yes, right? Okay, if you just notice it out, in this formula and in this formula, okay, J is here, J is here, E is here, E is here. Okay, so that means sigma is equal to, just compare these two formulas, from that you can get that sigma is equal to ne square tau by m. Okay, ne square tau by m. Okay, so I will just write it here, note as a note point. That is sigma is equal to ne square tau by m, and resistivity, conductivity is opposite term as resistivity, right? So resistivity is equal to, oh, this is m. Okay, so then resistivity is equal to m whole divided by ne square tau. Okay, you have to remember this as net by m, where for e alone you have to put square. So net net by m, net by m, bio. I've heard about biome. Biosphere? No. Aquarium? No. Something like that related thing, I think. But I've heard somewhere this word biome. Okay, so net by biome. Do not forget to e you have to put square. So or also you can take it as ne square tau by m. Okay, tau by m. That means what does the word tau mean normally in English? If a vehicle has stopped because of some sort of puncture or because of some sort of fault in it or drawback in it, normally we'll be asking some other two tours, right? So that is what ni tau me m me. Okay, so that means in ni means in Tamil it is actually you. Okay, ni is Tamil word. In English, if you just translate it, it means you. So you tau me. That's what it means. Okay, so sigma. Okay, so yeah, you can take it like that if you want. Normally we can use a lot of shortcut tricks to remember formula. So it's just like that. Like for an example, E is equal to V, naivid is equal to I, J is equal to nivida. Like that we are having a lot of things, right? Perfect. Then after this, what do we have? Then yeah, so here is the place where the most important topics all enter. Ohmic, non-ohmic, 3-mark questions of NCERT syllabus. Then after that we also have limitations. Then we have variation in R with respect to time. Okay, so first we will complete all these things. This first is resistivity of the conductor depends upon. All these relationships we are going to see in a single place. Very important point. Okay, so first, what is resistivity depending upon? It depends upon n. Okay, it depends upon number of electrons. Okay, sorry, nature. Yeah, n depends upon the nature of material. Hence, n is also depends upon the nature of love. Okay, so first is resistivity. Okay, first point is that resistivity is inversely proportional to n. Here n means what? It means electron density. Okay, n means what? It means electron density. In part 3 itself, part 3 or 2? In part 2 even we have discussed, I think, I don't know whether it was part 2 or part 3, but in there even we have discussed that n is electron density. Okay, so resistivity is inversely proportional to electron density because, for example, let us take that this is a conductor, and if this is having a lot of electrons, okay, a lot of electrons, and also n is directly proportional to, okay, n is directly proportional to number of electrons. Okay, and also all these values, okay, first of all this depends upon, okay, these two things is depends upon nature of the material. Okay, so nature of the material. Okay, see, for example, this is a conductor. In this conductor, in this per unit volume, okay, there is about 10 to the power of 29. Okay, 10 to the power of 29 electrons are there. Okay, if in case the count of electrons has got increased a lot, like it's more than 10 to the power of 29, and then in that case we can say that the flow of electrons will be also high, because number of electrons is also high. So that means resistivity will decrease with number of electrons. Okay. So this is what the first point is. Then what about the second point? Second point is that resistivity, yeah, so very important is that resistivity decreases with, resistivity is directly proportional to temperature. This is actually tau. Resistivity is directly proportional to temperature. Okay, temperature for conductors. Okay, for conductors. Okay, for conductors it is directly proportional, but for semiconductors it is inversely proportional. Okay, it is inversely proportional for semiconductors. Also, you have to note that resistivity is inversely proportional with tau. Okay, tau is what? What is it? It is just the relaxation time, right? In drift velocity, we are having Vt is equal to A into tau, right? That tau is what this tau is also. So it is actually inversely proportional because, wait, I'll be just explaining that concept also. I don't know why do I have to behave like this in such a cheapstick way for space. Okay, so coming back to this temperature thing, this tau thing, okay, relaxation time. Let us assume that this is a conductor, and in this conductor there are some amount of electrons. Okay, so for an example, let me take that this has an electron, this has an electron. Okay, this has an electron, this has an electron, this has an electron, this is an electron. Okay, like that there are many electrons in it. So this electron will come and hit this one. Okay, so the time that is taken between two electrons to hit each other, okay, just to collide with each other, we can say it as a tau. So if in case wait a second. Okay, so if you ask me how resistivity is inversely proportional to the relaxation time, very simple. We know that resistivity is directly proportional to temperature. See, this semiconductor thing at all we have not discussed now, but since I know it and I wanted to say to you all, I have said it. Okay, but coming to conductors, we will just take conductors, okay? See, but this isn't the appropriate explanation if you ask me. There is this frequency thing, there is this derivation at all. In Meta, I only checked, it said some things, but I couldn't understand them. But I have an alternative way of explaining this one. See, for an example, this is a conductor, okay? This conductor is actually having electrons in it. Okay, now we have started to increase the heat. Okay, now we have started to increase the heat. So as the heat increases, that means automatically what does it mean? It means the kinetic energy will also increase. Then what does it mean? It means that the velocity will also increase. So velocity of electrons will also increase. So okay, so that means if velocity of electrons increases, that means what? It means tau will decrease. It means what? Tau will definitely decrease. Okay, so yeah. So with increase in heat, now that means it is actually increase in temperature, right? Okay, so here temperature has got increased, which is in conductors. So in conductors now we have increased the temperature, so temperature is actually inversely proportional. Yeah, okay. So yeah, so temperature increases, then automatically what does it mean? It means wait, temperature is directly proportional to resistivity, right? Okay, and also resistivity is actually inversely proportional to relaxation time, because temperature is inversely proportional to relaxation time. That is why resistivity is inversely proportional to relaxation time. Okay, that is what the sequence is. Okay, ma. Next relationship is that going to be mobility. Also over here we are having some link to semiconductors, where we will be reading about holes. See, for an example, sorry, so this is actually proton. These are shells and subshells, okay, just shells. Subshells are very complex to be drawn. Circle and double only, but it's okay. We need not to represent them. Chemistry. Okay, see, here electrons will be there, right? Okay, so as they get energy, they get excited, they get to here, okay, they go to here, now they will be over here, right? Okay, perfect. Now, that means the electron which is over here has got energy, has got its energy, and then it has been to this particular point. So here in this particular point it is positive. In this particular point it is positive. Okay, it can be said as positive. Okay, so that particular thing is what known as Cole's mobility. Yeah, so that particular positive is there, right? Here positive thing is there, right? That is what known as holes. You will be reading in semiconductors. Okay, now coming to mobility, back to mobility. Well, yeah, I will be saying why did I say about this holes. Okay. See, if you ask me what is mobility, mobility is just this drift velocity whole divided by electric field. Okay, this drift velocity whole divided by electric field. Okay, so drift velocity divided by electric field is what mobility is. So for an example, if it is for a neutron, okay, sorry, if it is for an electron, then how can you represent this one? You can represent this as like this. See, what is this drift velocity is actually, we can say that it is small e, capital E whole divided by m into tau. Okay, into tau whole divided by capital E, right? So this E and this E can be cancelled out. So that means what? It means it can be said as just E tau by m. Okay, so E tau by m. So here this tau is there, right? This tau and then this m is there, right? So it is actually the main representation. Yes. Okay, so for electrons all you have to do is you have to put here E and here also E. Okay, then for holes you have to put in place of E H. In place of E you can just put H and you can just move on. Do not be stagnant in anything. One of the greatest mistakes that I have ever done in my life is to be stagnant. Okay, why am I giving you these life lessons where I am even struggling to live my life? Okay, So next thing is resistivity. Yeah. So resistivity and temperature. Yeah. So resistivity and temperature. This concept is very easy if you have read about RLS in class 11th. Okay, in class 11th, if you have studied RLS, we usually pronounce 11 as 11, right? 11 as 11, right? But it should be pronounced as 11. My English ma'am pronounces it like 11. So I will pronounce it like 11. Okay, if it's the correct pronunciation, I will continue. If it's wrong, comment in the comment section. Okay, so resistivity and temperature. If in your class 11th, if you have studied RLS, then this topic will be very easy for you, because in RLS it is there, for class 11th is there. Okay, so coming back to the concept, change in temperature is actually directly proportional to change in length is directly proportional to original length. Change in length is there, right? That is directly proportional to original length into change in time. Okay, into change in time. Okay, so here del L is equal to alpha. Okay, you have to remove this proportionality. For that, what you have to put a constant, and here the constant is what? Alpha. Okay, so alpha into L into delta T. So here alpha is there, right? This alpha is thermal coefficient. Thermal coefficient. Okay, so it is actually thermal coefficient. What is it? Del L is equal to alpha into L into del T. Okay, so this is something that you have to know. Just a basic concept, but it is not in our class 12th. Now we are going into class 12th concept. If you know this now, I personally feel like this concept will be very easy. Okay. So coming back to the concept, that is change in resistivity. Okay, change in resistivity. What does it mean? It means that there will be initially some sort of resistivity for any conductor. Okay, and the initial resistivity should be taken in 0 degrees Celsius. Okay, initial resistivity must be taken in 0 degrees Celsius. See, it should be taken in 0 degrees Celsius. Okay, and then you have increased some amount of temperature, then it would have got a new resistivity. Okay, wow. So this one is at some x degree temperature or degree Celsius also you can take it as. Okay, so yeah, so this is what it actually means. Okay, so yeah. Okay, so this is actually R1 and in this is actually R2. Okay, so here R1 can be said as R0. Okay, and this R2 can be as R2 itself. So we all know that in any delta T, okay, so in any delta, that means in any change, we will be always writing 2 minus 1 1D. We will be always writing 2 minus 1 1D, right? So here also it should be written as R1 minus R0. Okay, R1 minus R0. Okay, so del R is equal to, okay, so yeah, del R is actually directly proportional to what? First is normal resistivity and temperature. Okay, here temperature and then it will be T2 minus T1. Okay, so in order to remove this proportionality, I'm going to use the same thing as alpha. Okay, alpha only, that alpha and this alpha both are same only. So del R is equal to alpha into R into del T. Okay, so yeah. Now, if you just notice here, RT, okay, let us take this total delta R as RT itself. So RT will be, okay, RT will be equal to R naught. Okay, this is actually a different formula. We will be giving you this formula. How did it come? I will say. So you have got this formula, right? So from this formula, what can you write? So from this formula, alpha is equal to del R whole divided by R delta T. Okay, R delta T. Okay, well, so from this, what you can do, you can actually easily take in this space, you have to write R1 minus R0. Believe it or not, instead of writing R2 minus R1, write it as R1 minus R0. It will be very helpful. Okay. Alpha is equal to R1 minus R0 whole divided by R into T2 minus T1. Okay, so if you just bring this total thing to here, then that will be T1. Normally, see, what is this? What is this? This concept, okay, this particular thing alone I will be considering as delta T itself. Okay, so that means it will be alpha R into delta T is equal to R1 minus R0. Okay, so that means if you just want R2, okay, so I'll just bring this R0 over here. If I just take that R0 over here, that means alpha into R delta T plus R0 is equal to R1. Okay, so there R0, this R0 and this R is same. Okay, it is because this is also initial and this is also initial. This is also initial, this is also initial. Now note that it need not to be always at 0 degrees Celsius. R1 minus R2, right? Here R1, 2 minus 1 is the formula. Sorry. So here 2 minus 1 is the formula. So here 2 is this one and 1 is this one. Okay. So here 1 should be always having less temperature. 1 should be always having less temperature than 2. 2 should be having more temperature. That is the concept. Okay. So here this R and in this R will be same. They both are same only. So I can take it as alpha delta T plus 1 into R naught is equal to R1. Okay, into R naught is equal to R1. Like this, I can take it as. Okay, but in some cases, instead of R naught, they would have given R1, and here they would have given R2. That is also okay. I will say in when. See. Alpha is equal to, if this is very confusing, for you, I will just write it in a different way. This is actually correct only, but if this is very confusing, then I will just shorten that up. Okay. So this del R is actually R2 minus R1. Okay, and in this del T is T2 minus T1. Okay, so in this place, what I'm going to do is I'm going to just put definite formula, that is del R is equal to R alpha into del T. Okay, so here what I'm going to do is in place of delta R, I'm going to put R2 minus R1 is equal to R alpha delta T. R alpha delta T. Here, okay, here R1 and then R2 both are same. Sorry, R1 and R is same. Okay, R1 and R is same. So in that case, okay, so in that case, what can be done? R2 is equal to R1 plus R1 alpha delta T can be written, right? So R2 is equal to R1 into 1 plus alpha delta T can be written. So this is a formula. Okay, so this is a very important formula. Like this you can do. So or instead of that, okay, this is actually a major formula. Instead of that, also there is another formula that you have to remember. That's going to be resistivity. Okay, that's going to be resistivity. So all you have to do is, in place of resistance, you have to substitute resistivity. So R2 is equal to R1 into 1 plus alpha delta T. Is with respect to resistivity. Okay, and also you have to note this one point. That's note point is alpha alpha for metals, okay, and for semiconductors. Positive and then negative. Positive and then negative. Okay, so positive and then negative. Then after this, what is there? What else is there? Okay, so just if you just want a graph, you all know the graph, right? Just the proportionality graph, that's actually like this. Okay, or like this, or like this. Okay, like this you can take. For semiconductors, like this you have to take. Okay, yeah, so that's it. Okay, so next is this also another node point. This is also another node point. This is node 1. This is node 2. That is, see, if T1 and T1 and T2 are the temperatures and R1, R2 are the resistance. If these two are the temperatures and these two are the resistances. Okay, so here that means what? R1 is equal to R naught, okay, R naught into 1 plus alpha T2, okay, T1, here R1 na, here T1, okay, R2 is equal to R naught into 1 plus alpha T2, okay. So yeah, if you just have to divide these two, if they are just asking the ratio, then in that case the ratio is that R naught 1 plus alpha T1 whole divided by R naught 1 plus alpha R1 by R2. Okay, so this one and this one can be cancelled out, and then R1 by R2 is equal to 1 plus alpha T1 by 1 plus alpha T2. Okay, yeah, this is it. At last, if they're just asking the alpha, okay, yeah, what is R naught here? R naught is what? The 0 degree Celsius resistance is. Okay, so at last, if they're just asking the alpha thing, okay, if they're just asking alpha, what you can do, you can just put this alpha over here. Just you can take alpha as common, right? So if you're just taking alpha as common, how will you take alpha as common? Multiply. First, you have to do that thing. Okay, so R1 plus R1 alpha T2 is equal to R2 plus alpha R2 T1 is there, right? Okay, so take all the alphas, the terms which are having alpha to this side, and all the terms which are not having alpha to that side. Okay, so that means R1 alpha T2 minus alpha R2 T1 is equal to R2 minus R1. Okay, so here from this, if I just take alpha as common, so that means R1 T2 minus R2 T1 is equal to R2 minus R1. Okay, so if I just bring this term to there, then that means alpha is equal to R2 minus R1 whole divided by this term, which is R1 T2 minus R2 T1. Okay, yeah. So this is one thing you have to note. Okay, and at last, the last note point. Is that, see, this alpha thing is there, right? I have said that alphas, formulas, all these things, right? Also, you have to know this one point, that is RT, that means total resistance, or yeah, the resistance is actually equal to R naught. Okay, R naught, which means the resistance at 0 degrees Celsius into, okay, into 1 plus alpha T, okay, alpha T plus beta T square plus gamma T cube plus, like this, x on, it will be going on t to the power of 3, t to the power of 4, like this, alpha, beta, gamma, delta, what are the terms that we have, what are the Greek symbols that we have, everything will be just going on. But the thing is, the temperature that we are having, right, the change in temperature, right, that will be also decreasing. So you will be neglecting these terms, all these terms. So at last we are having here RT is equal to R naught into 1 plus alpha T. Okay. Then what we have here is limitations of Ohm's law. Oh God. What does it mean, limitations of Ohm's law? See, Ohm's law is not applicable for every device. Literally, Ohm's law is not applicable for the devices that we use, for mobiles, for computers, for laptops, for the smart boards. What are there? I think also AC, I don't know about AC, but for many concepts, okay? For many, not concepts, for many devices that we use in our day-to-day life, Ohm's law is not applicable, okay? So, the device is, first law, okay? V is equal to IR. V is equal to IR is not applicable. In board examination, in a 2-mark question, they have asked that prove V is equal to IR is incorrect, or it is not applicable for every device. Like they have asked, okay, one thing they have asked. Prove that V is equal to IR is not valid. So that is actually for not, it's not valid for every devices. It is not valid for some devices. Okay, so what are such sorts of devices? Those devices are known as non-ohmic devices. Non-ohmic devices. The devices which do not obey the law of Ohm's law are known as non-ohmic devices. Okay. They don't obey Ohm's law. Okay, so yeah, devices which do not obey Ohm's law are called non-ohmic devices. Very best examples are conductors, semiconductors. Sorry, not conductors. Very sorry. And also conductors are those which are, semiconductors are those which are highly used, not conductors. You have to note also this point, my your honor. It is because, wait, I will say, okay, semiconductors then after that vacuum tubes. What are vacuum tubes? I don't know what is vacuum tube. Okay, why it is not applicable? It is because resistance is inversely proportional to temperature. It is the main reason that we are using semiconductors a lot. Okay, if you don't understand the relationship between the resistance is inversely proportional to temperature and the usage, then just think a little bit. Okay, give some work to your brain, you will get it. Okay, and the graph for them, okay, the graph for them will be like this. Okay, so it will be like tan graph. Okay, it will be like tan graph. So it's like this. Micro ampere and then here it will be, sorry, here it is milliampere, micro, here it is milliampere, not capital M, it should be represented in small m only, and in here it will be microampere. Okay, here it will be microampere, which is 10 to the power of 6 minus 6, here it will be 10 to the power of minus 3. Okay, yeah, then after this is voltage, this side is voltage. Okay, if you just want to know that why is there such sort of difference, here it is milli, here it is micro, it is because of forward and then backward biasing. What is forward biasing and what is backward biasing? All these concepts we have seen already. I've explained them very clearly and I don't remember them again. I will do some quick revisions and I will come and talk about them to you. Okay, so this is the first point, that where Ohm's law is not obeyed. Okay, then the second point comes. Okay, then the second point comes. Before that, we have to see the difference between ohmic devices and the non-ohmic devices. Okay, so the first difference is that, see, it is actually Ohmic law. Ohm's law is applicable only at constant temperature and at constant strain, right? That you can write. Constant temperature at any temperature. Okay, at any temperature, no matter what, it will not at all obey. Okay, but this device is having some sort of discipline, at least with that temperature will be obeying, but this will not at all obey in any temperature. I don't care. Like that it is. Okay, we all have to be like this, not like this. Okay, then after that, the relationship between them is that voltage and then current's relationship is like this for them. Okay, like this is. Here it is square proportion, here it is just linearly proportional. Okay, yeah, here we are having very specialized famous formula. IR is equal to V is equal to IR. Here we don't have such sort of formula. V is not equal to IR. This is one of the important thing. Okay, so you have to write this one when they ask. Then secondly, you are also having this another concept that's actually this gas. Not, it's not actually gas, it is GAAS, which is current versus voltage for current. Okay, oh god, this voltage for, what does it mean? GAAS. That means, yeah, that means what? Here it means gallium. Here it means arsenic. Here it means what? Arsenic. Oh my god, my oh my goodness, my eye is burning. Okay, next is the graph. I'm drawing the graph. Okay, so yeah, it is just like elasticity. If you just compare this one, yeah. Also, I said now this one you would have studied in class 11th. Where is that? That this concepts you would have studied in class 11th, right? This is also I studied in class 11th in elasticity only, and also this graph is just like elasticity graph only. Okay, and also here if you just check it out. Also, this law is not, see, till to a particular limit only, V will be directly proportional to I. Then after that, it will not be directly proportional till to a particular limit only. Okay, that is what is explained over here. If you just check it out, here, okay, till this one point, till the bending point, you can say. Till here it is straight, right? So all the region which is straight, that is known as ohmic. First I'll represent what is x and what is y axis. So here x is actually voltage, okay, and I is current. And then all these three regions are non-ohmic. Okay, so it is actually non-linear region. Then it is negative resistance region. Yeah, it is negative resistance. I will write in a different color. Okay. The relation between voltage and current is not unique. That is there is more than one value of voltage for the same current I. A material exhibiting such behavior is gallium arsenide. Arsenide, it is not arsenic. Yeah, the same only. The relation between voltage and current is not unique. That is there more than one value of V for the same current I. So what they are saying is there is more than one value of voltage for just the same amount of current, it seems. Yeah, see, for the same amount of current itself, you just take in ohmic devices, it will be showing a different thing, and in non-ohmic devices, it will be showing different thing, right? For voltage, yeah, that is what is there, I think. I'm not a teacher, I'm just a student. So even if you ask me, I will be suggesting go and see some other persons who just teach professionally, as they have their what is that known as? Graduate certificate. Okay, next is power. The manpower, the woman power, the human power, the destructive power. What's power? What is power? Power is just some amount of heat, I can say. Energy. What is it? It's energy. So with this power, you will stop this particular concept. So yeah, no. We have to also see, before going to power, we will see resistance combination. Okay, combination of resistance. from our class 10th we are reading this, right? So this is going to be very easy one. Okay, see, I'm having here a circuit. One time in my class 10th examination, they have asked me this question. But what I did is, I didn't read for 3 resistors. I thought it was just for resistors. So I have taken 2 resistors. And I lost 1 mark for 3 mark questions. Actually, he should have given me 0 marks. But with courtesy and with the knowledge that I know this is a mistake and that I know the concept, he has given me 2 marks. Very great. Very great. Okay, so now coming to here, I'm going to take it as R1, I'm going to take it as R2, I'm going to take it as R3. Okay, so the current direction is going to be in this direction only, and we know that it represents the positive and we know that it represents the negative sign of the battery. Okay, so here what is constant? I is always constant in a series connection. Wait, I didn't even say what connection is this. This is series connection. I know you all are brilliant, so I need not to say it, but it's okay. Okay, this is series connection, and in here it says, okay, I is constant, and here potential difference VD diffs. Okay, it is different. So we have the formula. We know that what do we know? What is different that you have to take? What is different that only you have to take? Do not take what is common. So here VD is actually here V is same now. So V is equal to IR. We know that V is equal to IR. Okay, V is equal to IR. Then yeah, so proceedingly we can do these following steps. So V effective, that means total net voltage we can say, right? So that one can be written as IR effective. Since I is constant, we need not to put effective for I. Okay, so which is equal to first is IR1 plus IR2 plus IR3. Okay, ma'am. So from this I can take I as common. Since I is constant, I can take it as common. So I effective is equal to I into R1 plus R2 plus R3. So this and this can be cancelled out. At last, R effective is equal to R1 plus R2 plus R3. Okay, ma'am. I think I'm just using the word okay a lot, but I know that there won't be any reply. Because if I expect for reply, I will be termed as an idiot. Next is parallel. So, what is parallel connection? This is a circuit. Okay, so this is what the circuit is that we are going to take. So here this is going to be R1, this is going to be R2, here it is going to be R3. Okay, so here if the current comes over here, if the current comes like this, so here it will be splitting. Here the current will be splitting and at last will be joining here at back. Okay, so here what will be same? Here voltage will be constant in this point A, and then in this point B, if you just take it out, voltage will be constant. Then what is different? Current. Is different over here. So what did I say? See, first we are having the formula. We know that what is different current, right? So V is equal to IR. V by R is equal to I. So I is equal to V by I. V by R. I is equal to V by R. I is equal to V by R. V by R, right? So this is something that we know. So from this, what we can write? We can write that I effective, which is equal to V effective by R. Sorry, V by R effective is equal to V by R1 plus V by R2 plus V by R3. Okay, so which means from this I can take voltage as common, right? So that means what? I can just cancel this all out. Then it means 1 by R effective is equal to 1 by, no, I'll write this in a different color. What color did I use over here at last? I'll use here pink color. 1 by R effective is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is what we use for parallel connection. Okay. Next, at last, for power. We will complete this video with power itself. Okay. Oh my goodness. It's about to become 1. Wow. Power. So what is power? Power is the heat energy actually. We will just take power. Electrical energy. Power is also known as electrical energy. See, it is actually whenever electric current is passed through a conductor after some time, this indicates that electrical energy is being converted into heat energy. Okay, so electrical energy after some time will be definitely converted into what? It will be definitely converted into heat energy. Because of time. With respect to some time, electrical energy will be converted into heat energy as it passes in a conductor. Okay, see first what is power? I have to first reduce the word okay, then only it will be okay. Power is equal to VI. Here power is equal to VI. Okay, wait. I will first write with perfect terms and conditions. That means, for an example, let this point be point A. Let this point be point B. Okay, so in this one, there is Q charge and then there is R resistance. There is Q charge and then R resistance is over there. Now work done is equal to okay, so work done, which is W. What is work done? Work done is equal to VQ. Work done per charge. Okay, work done per charge is equal to voltage, that we know, right? So voltage is equal to VQ, and also V. So from this, what we can say, V is equal to so what is Q is equal to? Q is equal to IT. So from this, we can say that work done is equal to VIT. Okay, VIT. small t. Okay, big T always represents temperature. So work done is equal to VIT. Then after this, we can also say that work done per time. Okay, work done per time is equal to VI. So work done per time is here, right? So this is what known as power. Okay, this is what known as power. Yeah, so from this we can say that power is equal to VI. Okay, so VI is equal to, so V is equal to IR, right? V is equal to IR, right? So in this place I can substitute that other forms. For power. First main formula itself is power is equal to VI. Then power is equal to IR, I square R. Okay, power is equal to I square R is the next formula. Next is power is equal to I square R. So I is equal to what? We know that V is equal to IR. Okay, V is equal to IR and V by R is equal to I. So V by R. So in this place, power is equal to V by R the whole square R, which is equal to power is equal to V square by R square into R. So in this square and in this one can be cancelled out. This one and this one can be cancelled out. So power is equal to V square by R. Power is equal to V square by R. Next is heat energy. V square by R, V square by R. Next is heat energy. Heat energy is equal to, see, work done is equal to VIT, right? Work done is equal to VIT. So like that, energy which is heat, okay? So heat energy is equal to VIT. Okay, so from this with many other forms are there where I square RT is there. I square RT is there where V square by R into T is there. Very simple. All you have to do is you have to just multiply T with this. VIT, I square RT, then V square by R into T. That is what the difference is. Okay, so then at last, one kilowatt hour R is equal to what? See, kilo means 10 to the power of 3 into watt. Leave it as watt itself. R is actually 1 hour if you're just converting into seconds. So it will be 60 minutes are there in 1 hour, right? So which means 60 into 60 seconds are there. So which means that these many seconds are there, right? So I can write it into 36. This is so here 3.6 into 10 to the power of 6 joules are there. Joules are there. Next is electricity bill. Hereafter we are going to be the ones who are going to do electricity bill for our own homes. Okay. Well, if we do like that, we will be very good boys and girls. So no need. It will be done by electrician man even. They will do what is our work. Electric bill. But if we do the electric bill, maybe we can get less scoldings, as we are the one who's running a lot in our homes. I'm the one who's running 24/7 AC in my home. Yeah. So electric bill is equal to number of units into time taken. Okay, into time. Sorry, unit cost. Sorry, unit cost. And this unit cost will be given at the question paper itself, and this unit cost differs in the place with place. Okay, so number of units is equal to number of watts number of watts into time by 1000. Okay, into time by 1000. So yeah, from next concept, we will be starting cells very deeply. So cells is there, then combination of cells is there, then what is current formula for cells is there, then discharging of a cell, terminal potential is there, then at last we will be ending this whole lesson with the Wheatstone bridge. Okay, Kirchhoff law is also there. We will be also seeing Kirchhoff law with some sums. Then in other 30 minutes video of this lesson even, we will be studying about resistance, and also there is sums that we have to do based on Kirchhoff law and then resistance. Sums we will be doing, and we will end this lesson. Okay, so thank you, bye bye. I hope this video is helpful for one of you. Okay, bye. We will meet in another amazing video.